Here are solutions to 376, homework set number 11. This homework set looks at Z-transforms and digital filters. Kind of like saying that anything you do in hardware, you can do in software, and vice versa. In hardware, if I build a filter, I'm usually using Laplace transforms. Again, if I have a low-pass filter, for example, here's one circuit for a second-order low-pass filter with complex poles, something you cover in electronics. I have an op-amp circuit with two capacitors. This guy right here would let you implement complex poles with an op-amp circuit. Well, anything I can do in hardware, I can do in software. In hardware, I use Laplace transforms. In software, I use Z-transforms, which is kind of the whole point of this homework set. If I want to implement it using a microprocessor, I should really be using Z-transforms. So starting out, suppose I have a filter of this form. That would be in the S domain, that would be an op-amp circuit. Slightly different this one, but same idea. Part A, what is the differential equation that this represents? Well, to do that, I cross multiply. Note that Sy means the derivative of y. So S squared y is the second derivative, Sy is the first derivative, y is just y. Sx is the derivative of x is just x. So this is the differential equation that represents that transfer function. And you can almost see it by inspection. The denominator polynomial is the differential equation for y. The numerator polynomial is the differential equation for x. Sometimes we use prime notation just because the d squared by dt squared is kind of a pain to write. And a lot of word processors don't do that. Prime, it means derivative. So this is the second derivative, 2 primes. First derivative, 1 prime. No derivatives, just y. Another way of writing it. Either way is correct. Part B. Suppose my input is a constant and a sine wave. Find y of t. Well, this is where we use superposition and linearity. What linearity means is that if I have f of a plus b, that's equal to f of a plus f of b. That's a linear system. So if I have two inputs, I'm going to treat that as two separate problems. One where the input is 2, the second problem where the input is 3 sine of 4t. Take the two answers, add them together. That's the response for the input being 2 plus 3 sine of 4t. So starting out, if the input is 2, then everything's e to the st. S is the frequency, j omega. Frequency is 0. E to the 0 is 1, so this is 2 times 1. Usually the 1's not written, but that's kind of what it means. So S is 0. The representation of the number 2 is the number 2. Surprise, surprise. So this is the gain everywhere. All I care about is what's the gain at S equals 0. Times the input at S equals 0 gives you a real number. What that represents is a constant, 0.9333. Second part, when the input is 3 sine of 4t, S is j4. The input is 0 minus j3, real part's cosine, minus j is sine. Y then is the gain. This is the gain everywhere. All I care about is what's the gain at 4 radians per second, times the input at 4 radians per second. 0 minus j3 gives you a complex number. Real part's cosine minus j is sine. Add the two together, and you get the total answer. That's in Laplace. In the z domain, I have a transfer function relating x and y. But this is in function of z. What z means is the next value. And get a difference equation, different than a differential equation. And to see that, let's cross multiply, multiply out, and zy means the next value of y. So z squared y is y 2 samples in the future. Zy is 1 sample in the future, y is just y. Zx is 1 sample in the future, and x is just x. So this is the difference equation that represents that transfer function. And different than a differential equation. This is a difference equation. And you can kind of see it by inspection. The denominator polynomial is times y. The numerator polynomial is times x. Now sometimes people don't like using the future value, so I can do a change in variable or a time shift and shift everything by 2, in which case this becomes y of k minus 1, y of k minus 2. Either form's correct. It's whichever your preference is. Part B is if the input is a constant and a sine wave, find y of t. Well, this is just like we did before. Use superposition, treat this as two separate problems, but the difference is z is e to the st. For j omega, that means z is e to the j omega t. Just a complex number. Oops, misspelled t. So, when x is 2, s is 0, z is e to the st, or z equals 1. The phasor representation of the number 2 is the number 2. This is the gain everywhere. Find the gain at z equals 1 times the input at dc gives you a number. What that represents is a constant. At dc, y of t is 12.5. Repeat for the AC term. When x of t is 3 sine of 4t, s is j4, z is e to the st, e to the j.04, a complex number. X is 0 minus j3, real parts cosine minus j sine. Now y of t is, here's the z. What's the gain at z is e to the j.04 times the input, gives you a complex number, real parts cosine minus j sine. The total answer then is dc plus ac. And part C is if the input is a step, this is the gain everywhere. What's the gain when the input is a step with an amplitude of 3? So here's the step times 3, step with an amplitude of 3. To solve that, what you do, trick in the z domain, is pull out a z, do partial fraction expansion, bring the z back. Now this is in my table. This is 18.75 times a constant of 1, minus 48.75 times 0.8 to the k, plus 30 times 0.7 to the k. There's y of k. To convert from the s-plane to the z-plane, there's a couple ways of doing it. The approach I like using is z is e to the st. That's the mapping from the s-plane to the z-plane. So problem 3 is if I have this filter in the s-plane, what is the discrete time equivalent? So in that case, if I know t is 0.01, I need to know that. To convert from the s-plane, I go e to the st, so s is minus 1 becomes a pull at 0.99 in the z-plane. Minus 6 becomes 0.9418 in the z-plane. Minus 12 becomes 0.8869. So I've got 3 poles in the s-plane, I've got 3 poles in the z-plane. To find k, just match the gain anywhere, typically dc. At dc, the gain of g of s is 6.94. Pick k so g of z has the same gain. Solving, I get k is 0.0004. So here's g of z. Kind of a sidelight, if I implement this, I've got a little bit extra delay in g of z versus g of s. Has no effect on the gain versus frequency, but there's extra delay in the system. What I could do is add z's in the numerator, trying to match the delay. You're not going to get it exact, so just kind of trial and error. If I add 1z, 2z's, 3z's, that shifts it in time. Going forward, gets rid of the delay. How many z's do I have to add to make these two closer? This is a little bit more accurate, a little closer. But again, delay has no effect on the gain versus frequency. This is a perfectly valid answer. Same gain versus frequency as g of s. To see that, what I can do is plot gain versus frequency. In MATLAB, let's go from 0 to 20 radians per second. G of s is j times omega. S is j omega. Then g of s is the way you write it. 500 over s plus 1 times s plus 6 times s plus 12. Using the dot notation to tell MATLAB these are 2,000 separate calculations. Do each one separately. That's g of s. To get g of z, t is 0.01, z is e to the st. G of z is the way you write it. 0.0004 divided by z minus 0.99 times z minus 0.94 times z minus 0.88. Plot the two together, g of s in blue, g of z in red, and you get this. The two filters have basically the same gain versus frequency. The two filters are equivalent, meaning from a practical standpoint, I don't really care. Implement it in hardware as g of s, implement it in software as g of z. Both behave the same. That also works with complex numbers. Problem 4, if my poles are complex, here's the poles in the s-plane, poles in the z-plane. G of z has 3 poles s-plane, 3 poles z-plane. Match the DC gain, pick k so the two have the same DC gain. Here's k. Here's your filter in the z-plane. Now if you don't mind complex numbers, write in this form. That's how I prefer it. Some people don't like complex numbers, so they multiply these out. Puts that in a polynomial. Either way, pick your favorite. As a check, plot gain versus frequency s-plane, gain versus frequency z-plane. In the s-plane, here's my poles. In the z-plane, there's my poles. Z is e to the st. Here's the DC gain s-plane. Pick k to have the same DC gain. K matches the DC gain in the z-plane. Plot gain versus frequency s-plane. Plot gain versus frequency z-plane. The blue line is g of s. The red line is g of z. Same gain versus frequency. It's the same filter. Now the reason we're doing that is once I have the filter in the z-plane, implementing it in software is really easy. Here's my filter. One way to implement it is multiply out the polynomial, cross multiply, find the difference equation, do a time shift to make it causal, solve for y of k. Here's the difference equation that corresponds to this filter. That's your program. So what I do is in software, I remember the last 3 inputs, read the current input, remember the last 3 outputs. Here's the current output. That's my program. With the k, k minus 1, k minus 2, translated to a variable that C won't complain about. Presumably, once I calculate y, do something with it, like spit it out to a D to A converter. Wait 10 milliseconds, that's my sampling rate t, then repeat. That's why we like the z-plane. I can implement a filter in the z-plane exactly. Problem 6 looks at another type of filter called an FIR filter. What an FIR filter does is I remember the current input, the last input, and the last 200 inputs. I then create an output by saying the output is a function of the current input, something times previous input, so on. It's the impulse response times the last n inputs. So if I can find the impulse response of a filter, I know how to implement it as an FIR filter. To illustrate that, let's design a filter with this gain versus frequency. Now that'd be really hard to do with poles and zeros in the S-plane. Pretty easy with an FIR filter. To do that, I need to find the impulse response. So from the lecture notes, the impulse response of a filter with a corner at a radians per second is 1 over 2 pi sine of AT over t. So here's a low-pass filter, corners at 2 radians per second, gain is 3. So multiply by 3, make a equal to 2. Then here's another filter, gain is 1 out to 6, minus a filter with a gain of 1 out to 4, gives me this response. Added to the previous one. So here's the impulse response. It's 3 sine of 2t over t times 1 over 2 pi plus sine of 6t over t minus sine of 4t over t divided by 2 pi. That's the impulse response of this filter. What that looks like is in MATLAB, let's just go from minus 20 to plus 20 seconds, somewhat arbitrarily, shift it by a hair to avoid divided by 0. Here's your G of S, that's the impulse response. Plotting it, that's the impulse response of this filter. I may not like it, but that's what it is. If I could write a program that has the same impulse response, I get the same filter. Now the problem with that is this is non-causal. It goes to minus infinity to plus infinity. Infinity is a tough number, so let's say anything past 20 right here is 0. I'll ignore that. Anything beyond plus 20, I'll ignore. I'll give it a 20-second delay to make it causal. And pick a number of points. I'm going to represent that with 200 points, somewhat arbitrary. 2 is too few, 2 million is too many. Pick a number between 2 and 2 million. I chose 200. If I do that, there's the impulse response I'm implementing. A little bit different, but close. To see what the actual frequency response is, I will add up all the frequencies. So here's my impulse response. The frequency response is the first impulse times 1, second impulse, h of 1, times 1 over z squared, 1 over z cubed, and so on. S is j omega, z is e to the st, so here's 1 over z squared, 1 over z cubed. Add them all up. Here's the actual frequency response of my FIR filter. What's kind of impressive is this is pretty darn close. The gain is roughly 3 out to 1 radian per second, roughly 0, then roughly 1, then roughly 0. It's almost right, a little bit wrong, but that's because I didn't use an infinite number of points, and I didn't go from minus infinity to plus infinity. But with what I did, this is what I get. Get a fairly close approximation. That's an FIR filter. So that is homework set number 11 for 376. I can implement filters in the S-plane. That's using op-amp circuits, stuff you do in electronics. I can implement filters in the Z-plane. That's 376 embedded systems. If you want to implement a filter in the if you want to implement a filter in software, you really should be using Z-plane. And I can convert from the S-plane to the Z-plane, or I can also do an FIR filter. A couple different options. And that is homework set number 11 for 376 embedded systems.